Okay, you're all set.
All right, thanks, Jim. So hi, I'm Jake Izraelevitz. I'm the PI for our Venus balloon tech development here at JPL. I'm presenting on behalf of a very large team, not only at JPL, but also at WashU and Near Space Corporation, who's a balloon manufacturer up in Oregon. They actually do a lot of high altitude balloon drops for aerospace, like the ExoMars shoots, for example. So it's a real pleasure to be able to work with the professionals for putting these types of balloons together. Next slide. So we've been developing these balloons for an aerobot mission to the clouds of Venus. These are very well suited for a long duration type of exploration. You get to avoid the surface conditions, which are very harsh. You get to live in atmospheric densities and pressures that are quite similar to what you see at sea level on Earth. And there's plenty of sunlight. So you can, if you have a solar powered mission, you last as long as the lifting gas stays in the balloon. Now, while these conditions are relatively clement, there's enough quirks of the Venus clouds that you do need specialized balloon designs for surviving in the Venus clouds. Not just any balloon will do. The temperatures are a little higher than what we usually design balloons for. There are, of course, sulfuric acid aerosols, and so you need to be resistant to that type of corrosion. When you get blown to the dark side of the planet, you'll be there for about 70 hours, and so you need to carry enough battery capacity to last on that dark side, which costs mass. And then, of course, the Venus atmosphere does move a lot. There can be sustained vertical updrafts and downdrafts of up to 3 meters per second. And so our balloon designs are, have enough stability margin in order to compensate for that type of disturbance. Next slide, Jim. So we've been developing a very particular type of Venus variable altitude aerobot. We are aiming for long duration. So at this point, we think we can last for one Venus solar day. That's 117 Earth days, given today's balloon technology. So balloons of this type actually have flown for 3 times that long on Earth. So we think that's quite feasible. And we've been speccing our materials to hit that requirement. If you last in the Venus atmosphere that long, you can expect to go around once every 3 to 5 Earth days. So this is many circumnavigation over the course of the mission. Our balloons are passively stable in altitude. So if they get pushed down, they gain buoyancy. If they get pushed up, they lose buoyancy. And so we get to keep a relatively fixed buoyancy, even if the we lose power or lose comms. You can expect the balloon will still be around when you reestablish comms. So even though we are passively stable, we can actually move what that equilibrium altitude is. And we do this by moving gas between chambers. So we can descend slightly slower than we ascend. And so over the course of the mission, you can expect us to be moving around between 52 and 62 kilometers. The goal is at 10 kilometer wide altitude range for Venus. And finally, balloons are by their very nature very scalable. You make the envelope bigger, you can carry more mass. And so we now have point designs that have closed between a 15 kilo carry capacity to all the way up to 200 kilos. And this is in support of certain decadal study concepts, for example, that we've been providing balloon designs for. Next slide. So the architecture we use on Venus is what we call a balloon-in-balloon architecture. So it's 2 chambers. The outer balloon is essentially a big bag of helium gas. It's slack, and so the pressure inside that balloon is same as outside. But then inside of this outer balloon, we have an inner chamber, and this is essentially a large tank. And by pumping helium from the outer chamber to the inner, you decrease your volume, and so you go down. If you open up a vent between the 2 chambers, your volume increases and you go back up. So this requires about a 4x change in volume between the top altitude and the bottom. And of course, we have margin on top of that if you get blown outside the altitude range. But that gives you an idea of how much scale of volumetric change you can expect of this type of balloon. A nice quirk of this design is that because your outer envelope sees the acid but doesn't see high pressure loads, whereas the inner balloon sees the pressure loads, not the acid, you can be more strict about what types of materials you use for those types of envelopes, and so that eventually saves you mass because you can specialize them more. Next slide. Okay, so this balloon looks really great, but how do you actually start the flight on Venus? If you click once more, this video will play. The part of the entry sequence that usually gives folks heartburn is this middle phase where you need to get the balloon out of its container and extract it. So this is actually something that JPL has done a lot of work in back during the Valor program days. These were discovery proposals in the mid-2000s. And the trick here is that you don't actually use the balloon to arrest the snatch load of the parachute. So we use an external load line, and that's what's slowly reeling out the parachute. And only once the balloon is all the way extended do we transfer the load to the balloon, and then we start filling it up with helium gas. And so we don't land on Venus before we inflate. We actually inflate midair. And so a lot of our work on these multiple chamber balloons has been figuring out, can we still inflate them from this type of hanging configuration, because that's what we need to do when we get to Venus. The inflation timeline of actually getting the gas in is about 10 minutes. Next slide. Okay, so our balloon development is on 3 main thrusts. The first is that we are building prototype balloons out of the actual flight materials we plan on flying on Venus. These are resistant to sulfuric acid and the optical environment, the temperature environment and such. This left photo here is an example of some of our acid testing, where we have high concentration sulfuric acid on one side and witness strips on the other, and putting this in ovens and making sure that our seams are able to actually withstand the environment. We're also now moving into doing acid aerosol chambers. So Mike Poggin had a nice talk yesterday on some of the developments of aerosol chambers at Caltech and JPL. Once we build these balloons, we do fly them. So we fly them in the same air densities as we expect to fly on Venus. These are about 1/3 scale prototypes. And we also use these prototypes to demonstrate the deployment of inflation technologies. And then finally, we do a lot of modeling work. So we validate those models against these test flights and the deployment tests. And then we use those models to predict what full-scale balloon performance will look like when we get to Venus. And this is using a code base out of the JPL DARTS lab. Next slide. So at this point, we've made a couple of these Venus prototypes. We keep increasing the fidelity and increasing the size as we make larger and larger balloons. At this point, we've made 2 of them to date. We're planning a 3rd one this summer, and then next year, we're actually going to be doing our full-scale build. This second balloon here is what we've done a number of test flights on, and so I'll mostly be focusing on this one balloon. It's designed for the full temperature range, and it's made out of the materials that survive the sulfuric acid. Next slide. Okay, so I'm happy to say we had a couple of successful flights in a hangar last, I guess, a year and a half ago in August. These are about 22 flights in the still atmosphere, and we use this as sort of a training run to make sure that we could get really good model match between our first principle dynamics and what we actually observe in the hangar. We also use this to deploy from a hanging configuration. Next slide, Jim. This is showing a couple of stills of what that inflation looks like. So, we extract it using the crane and then start putting gas in. So at this point, we're quite comfortable doing these inflations from the hang. There's actually an awarded SBIR phase 2 at Near Space for doing more dynamic extractions. And so I'll be happy to talk about that hopefully at the end of the year. Next slide. But of course, once you're done doing flights in the hangar, you do actually have to fly outside. And we finally were able to do that this past summer. So this is my favorite photo from the test flight campaign. So you can see 3 very nervous engineers. And the reason we're nervous is we're about to put gas in the balloon. And once you do that, it's actually quite hard to get the gas back out. It is a gas-tight membrane. So it's sort of a point of no return. But the reason we took this photo is, if you hit next slide, it turns out that directly downwind was Venus. And this was totally an accident, but clearly a good sign, because we get the balloon up and Venus is directly downwind. You can just get blown straight to Venus. You don't need the rocket. Anyway, next slide. We did have 2 successful test flights, got the balloon down back on the lake bed both times. We ground launched in 50-mile-per-hour winds. During the flights, we were able to demonstrate altitude control of a 1 kilometer wide band. So getting on our way to 10 kilometers, we've only done 1 kilometer so far, and this is actually at the densities that you would expect in the mid-clouds on Venus. This balloon is actually still in good condition. We inflated it again a couple of weeks ago, and we're putting together an AAA journal paper on test data from that flight. So I'm not going to show that data this talk, but I will show some clips from the flight. If you go to the next slide, Jim.
Yeah, you got to wrap up quickly here.
Okay, sounds good. Well, this is my last slide. So this compendium of clips from that test flight and bullet points that can be my conclusion. So I'm happy to take any questions while this is playing.
Jacob, you've got us all emotional now.
Yeah. So Paul Byrne put this video together, so you can thank him. We had a nice drone pilot for the photography.
We do need to move on.
All right.
So, thank you.